All right, are we ready to get started? Okay,
Sure.
welcome everybody to the APS Journal Club. I'm Steve Brunton, and it's my absolute pleasure to moderate today's Journal Club. We're going to hear about a really fantastic new paper, Machine Learning and Fluid Dynamics, a Critical Assessment by Kunihiko Sam Taira from UCLA, Georgios Rigas from Imperial College London, and Kai Fukami from Tohoku University. And it's my great pleasure to introduce Professor Taira, who is going to give today's lecture. So before my introduction, just the format of this journal club, there will be a 15-minute presentation by Sam, followed by a 15-minute Q&A. So throughout the talk, if you have questions, please put them into the chat. And then at the end of the presentation, I'll moderate and Sam and co-authors will be able to answer the questions. So we really have a treat today. Professor Taira is one of the world's leading experts in machine learning applied to fluid dynamics. He has won numerous teaching and research awards, including the Navy and Air Force Young Investigator Program awards. He is an APS fellow in the Fluid Dynamics Division and was awarded the Vannevar Bush Faculty Fellowship, which is the highest honor in Department of Defense research. So really just a world-class researcher, and it's our pleasure, Sam, to hear your take on this critical topic. So please take it away.
Thank you, Steve. Thank you for a very kind introduction. And it's nice to see a very friendly face. Steve is a long-term friend of mine, so thank you. It means quite a lot. And I thank the committee for inviting us to talk about the paper that we recently put together. This presentation that I'm going to give is based on a perspective paper that George Rigas at Imperial College London and Kai Fukami has put together. This is based on a lot of discussions that we had over the years with our colleagues and amongst ourselves. So I think there's been a lot of thoughts that's been placed into it, and we look forward to receiving feedback on this topic either today or we'll also be at APS. Okay, so let me get started. Now, before I get started, if I can start this thing, hold on. Here we go. Let me acknowledge a few people. During the compilation of this paper, we received a lot of feedback from these 5 people, and we really thank the feedback that strengthened the paper. We also thank Beverly for inviting us to put this perspective paper together for physical review fluids, and also our sponsors for enabling us to work in the area of machine learning for fluids and to organize workshops over the past few years that made this paper cohesive. Okay, so again, let me mention that this is going to be a slightly different type of talk that I will give today. It's not going to be super technical. It's going to be very general in the discussion. So again, it'll be quite interesting to see how it will go. But let me talk about fluid dynamics, right? So fluid dynamics is really based on a study of flows, right? It's physics, but there are multiple disciplines or sub-disciplines that make this study possible. Theoretical fluid dynamics is one. There's also experimental fluid dynamics and also computational fluid dynamics. Now, we have all seen that there's a 4th field or subfield that has grown tremendously over the past decade, and that's the data-driven fluid dynamics, which has also been enabled by the amazing growth in computational resources and also the computational, let's say, libraries. Now, slightly different from the other 3 fields is that data-driven fluid dynamics is dependent on getting data from other fields. And we need to really work closely with experiments and computations, right? Okay. Now, I've written the arrows to go to data-driven fluid dynamics, but this is not really a one-way street. It can go the other way around too. And also that the insights that we get from theoretical fluid dynamics is also quite important in developing, I would say, physics-driven, data-driven fluid dynamics techniques. Okay. Now, these boundaries that we might see on this diagram are starting to become blurred, right? There's a lot of crosstalks across these disciplines, and there's blending of these fields. Okay. All right. Now, it's been amazing to live in this era to see all the amazing developments and achievements that machine learning has made in the field of fluid dynamics in terms of how it's been used. It's been used to model, predict, and control a wide range of flows. And here I'm just going to list a few things that are, I think, indicative of how amazing some of these efforts has been. In some cases, machine learning has outperformed some of the traditional techniques, but there are also challenges that lie ahead of us, right? There are some problems that are still challenging for us to tackle, okay? Now I'm going to talk about a review of machine learning for fluid dynamics. My colleague Steve and his colleagues, along with Karthik, has written 2 amazing review papers on this topic. So I refer you to look at these, okay? Now, what we're going to talk about today is what are the outstanding challenges in hopes of stimulating discussions to support future machine learning research and educational activities in fluid dynamics, okay? That's going to be the effort of this paper and also this talk. Okay, so let's talk about the state of affairs right now. Okay, so I think all of us, or many of us, go to APS DFD meeting. And if you count the number of abstracts that has these keywords like machine learning, deep learning, or data-driven techniques, you'll see that from around 2012 or so, the number of these abstracts have increased quite a bit. Now, since about 2020, the numbers of abstracts have sort of stabilized, right, as you can see. Now, I don't think that means that the number of machine learning applications has gone down. In fact, it has gone up quite a bit, probably. And if you also look at the number of conferences and workshops that's been held since then, it's growing tremendously. There are a lot of opportunities to exchange ideas and present your ideas at these conferences, okay? Now, so the initial ramp-up phase of machine learning and fluid dynamics is appearing to stabilize, right? So now I think we're in this transitional phase. I would call it we're in the teenage years, right? So if we want to make these machine learning more into the mature stage, what should we do next, right? And the questions that we're posing here or asking ourselves is, what are the outstanding challenges in machine learning for fluid dynamics? That's the topic of discussion today, okay? Probably should speed up, but okay, right, let's see. All right, so here are the 6 outstanding issues, maybe issues or discussion points that we have identified, okay, that we're going to talk briefly today, but also if you want more details, they will be in the paper. Okay, so the formulation, this isn't really an issue. Of course, this is a mathematical formulation or problem, but generating a machine learning model from some data is what you generally want to do, right? And these will come from experiments or simulations. And the idea is that you want to come up with a machine learning model F with some parameters theta, and you have some input and output, right? Input and output will depend on the problem that you're looking at. And generally, to solve for or find this machine learning model, you have to solve some kind of optimization problem. And that would involve some sort of loss function. And you need to tune the parameters so that you can determine this machine learning model. What has made machine learning really popular is the rise of deep learning type techniques, oftentimes put on a neural network. And that could be an architecture that could be used for F. Okay. Oftentimes, this loss function can be chosen in some appropriate ways, where you would have the input and output relationship based on training samples. You can also add regularization terms that would sort of force or encourage certain types of behaviors. That could be sparsity, or it could be, let's say, trying to satisfy certain types of physical constraints. Okay. All right. And there's usually some hyperparameters that you have to worry about. Okay. Now, let me talk about what we can get possibly from these, and that's talking about gaining insights, right? And there's truly a hard question here is like, okay, does machine learning really deepen our understanding of fluid physics, right? And when we ask this question, what does gaining insights really mean? Okay, we have to be kind of honest about what gaining insights really mean, but generally means, are we uncovering something new and fundamental? And those of you who might be interested in publishing these results, these are some of the important questions you have to face if you're trying to publish or make headways in the field of fluid dynamics. Oh, I'm hearing someone speak, all right. And another thing that's important is the discovery limited to the training data, right? Is it just a one-off thing, or is it going to generalize, right? So here are the things that I just mentioned. And deepening physical understanding requires a holistic view with fluid dynamics. So you can't just stay in data-driven fluids. You have to look at this from a much broader perspective involving experiments, computation, theory. Okay, so you have to have a good balance view of fluid dynamics to make headways here. And let me also say that interpretability of the results will evolve, right? I can name a few things that used to be thought as very difficult to interpret, but nowadays understood to be really rigorous and understanding, right? So this type of results will evolve, and I'll look forward to seeing some of these interpreted results that machine learning will provide in the future. Okay, now let's also talk about generalizability of the model, right? This is also a major issue that is outstanding, right? And what really we want is that we want to make sure that the models and the results that we obtain need to be checked beyond the training data sets, right? And that usually relates to the concept of whether you have an interpolation or an extrapolation. So here's kind of an example that my co-author, Kai, and I have looked into about turbulence. And we said, well, can we look at time or Reynolds number as a measure of interpolation or extrapolation? That's really not a good measure, right? You, in fact, have to find a new axis to make sure that you can have interpolation or extrapolation, right? Now, there are also some other techniques that seem to be promising. For example, you can use transfer learning or foundation models to see if you can have some trained models that could be applied or adapted efficiently to other types of conditions or fine-tuned in some way. So I think this is probably going to be a really big research question that could motivate some interesting new research in fluid dynamics. Another thing that we also need to consider is model complexity, right? We have this beautiful equations called the Navier-Stokes equations. Usually fluid flows are described in some parsimonious ways. And I stole that word from Steve, right? We've been hearing him talk about this, okay? And the recent trend, this is a little bit concerning to me and many of us, is that sometimes we see a rise in overly complex models enabled because that we have these computational powers and resources. So I would call that a let's try and see if it works mentality, right? And of course that will work, but it'll be a bit silly sometimes. And here's a little silly thing that I put, asked ChatGPT what it thinks of a overly complicated machine learning model, and that's what they produced. And I can name many works that would produce a much more complicated machine learning model to see if it'll do something very simple. So we got to be mindful of that, okay? Now, sparsely promoting techniques might be able to sort out what's important, what's not, right? And capture the important physics. And we're going to do all this so that we avoid machine learning models to be a black box tool. And this is something that's also been told, not just about machine learning, but also about CFD. So I think a lot of things can be translated here. Okay, now let me talk a little about data and codes, right? And I think I'm going to run out of time, so I'm going to go through this fairly quickly. But we need really high quality data. And I think CFD and experimental people are really good at making sure that they're good. And it has to cover a diverse set of flow regimes. Okay, so for example, we can't just keep feeding low Reynolds number flow and hope that the machine learning model will work for high Reynolds number flow. That in general may not be a great approach, right? Although there might be some ways to take advantage of some certain scaling, but in general, you want to make sure that you have a diverse flow regime here, right, covered by the data set. You want to make sure the data is also good because machine learning models can pinpoint that you might have an error somewhere. Okay, there are some excellent databases. Johns Hopkins Turbulence Database, it's been with us for a while, but that has served a great purpose in terms of advancing turbulence. And we might need something that captures unsteady flows and much wider range of data sets. Now, this, in my opinion, I think in many of our opinions, is a national treasure, right? This is a national resource that when it gets funded, it's kind of silly to just do it one-off and then forget about it. I think and I'm not talking about machine learning, but from a computational experimental side, when you get data, you might want to think about the long-term use of these data and how it could impact the community with the machine learning in mind, okay? Same thing with coding. We should be thinking about how to share these codes so that it's transparent in the way we do research, okay? And that requires a lot of verification, validation, and uncertainty quantification standards that in some rigorous ways. And I think we can mimic how CFD and experimental people have done this over the years, okay? Now, another thing that I want to also mention here is that creating the data is not free, right? High quality data should receive proper credit here to make sure that their quality is to understand and acknowledge that their data is coming from major scientific contributions. Okay. Right. Now, I think the last part of my talk of those 6 outstanding issues is education, right? And we need to integrate physical understanding into data-driven methods. So we want to foster education that bridges all disciplines here. Okay. And it goes both ways. Another thing that is interesting here is that the amount of enthusiasm for machine learning has raised expectations in fluid dynamics. Sometimes it's great, sometimes it's a little too much, right? And there's also a generational gap in machine learning literacy. I was surprised to see some high school students even getting really into machine learning before they even join college. And in college, a lot of students are getting into machine learning classes. And I must admit, when I was in college, I did not take machine learning, right? So there's a bit of a gap that needs to be filled, right? So I think when we talk about educational programs and workshops, we need to target varying level of machine learning familiarity, okay? And we need to mix these people together so that we can enhance collaborations across generations, but also to make sure that we can incorporate theory experiments in CFD, okay? We also need to do this across the academia, industry, and government because they will have different objectives, but only when we have a healthy understanding of machine learning and how it could advance our field, I think then we can start talking about how we can translate from basic research to applied research using machine learning, okay? All right, so these are my final remarks. I'm gonna summarize my talk, right? We've seen a large number of success stories with machine learning. It's really exciting. And as we try to advance our field further, we offer this critical assessment, and we're not trying to be critical of machine learning. We're just being fair, and we're offering this assessment to encourage further advancement of machine learning. We're in fact a huge supporter of machine learning here. And those 6 outstanding issues that we discussed were formulation, insights, generalizability, complexity, data and code sharing, and education, right? And we need to think broadly. I think, and the chief editors can correct me, but I think if we can address some of these outstanding issues with some of the new techniques, they might fall nicely into the new section of PR Fluids called NEAT. That's meant for these new algorithms that could be groundbreaking, okay? So we hope that this paper, this perspective paper and this presentation stimulates a lot of discussions and inspire new research. If you're interested, here's the paper that we wrote. It's available on Physical Review Fluids again. I'll end my talk now and welcome your questions. And if it doesn't fit within this presentation today, I'll be at APS and I'll be happy to continue the discussion there. Thank you.
Wonderful. Thank you, Sam. And yeah, what an interesting perspective. So if anyone has questions, please feel free to raise your hand on Zoom. I'll start with the questions from the chat. And Sam, I'll just read out the first couple.
Sure.
Good. So the first question, how much better is the extrapolation capability of modal analysis techniques like DMD or maybe LSA and resolvent analysis compared to machine learning methods like PINs? How much better do the modal analysis extrapolate?
I mean, that's a difficult question to answer, I think. But if you're talking about modal analysis from a linear perspective, these modes could change over operating conditions, right? So if that is not of a big concern, I think they'll do okay. But if that's something you don't have in your training data, you have to think carefully, right? And if you're talking about nonlinear machine learning, they tend to do okay, extrapolating slightly outside of where you are. But again, you need an axis to say what is interpolation, what is extrapolation. I think if you can capture that effect, then you can safely do a little bit of extrapolation, but it wouldn't really be an extrapolation, it'll be an interpolation on some axis. Yeah, sorry, I don't think I answered that very elegantly, but I'll be happy to talk more about it.
Another question, POD modes, I believe, are easy to interpret because the output is reconstructed via linear combination. How about modes, for example, from autoencoders with nonlinear activation functions? How do we interpret them and gain physical insight?
Yeah, all right. This is a really interesting example. So POD didn't used to be considered interpretable, and until I would say a decade or so ago, or maybe a couple of decades ago. So that's interesting, right? And if you talk about nonlinear modes type analysis that you would get from autoencoders, I think we're starting to get more insights into it. I think Kai can maybe provide some more insights into it, but his group, along with Professor Fukagara's group in Japan, have made some headways in that. And I think if you also look at the results that you get from an autoencoder, if you incorporate physics into it, some of the results can be interpretable and provide a lot of insights.
Thank you. Let's take some questions from the live audience. Pranshul, you have your hand up. Would you want to unmute and ask a question?
Yeah. Hi, I'm a graduating PhD from Purdue. Thanks a lot for the talk. And you mentioned these 6 big issues. And I think some of these issues are also correlated, that how do we even prove that we have achieved some degree of generalizability, right? So we need like large amounts of well-annotated data sets that should not be coming from like one own lab. So are there any large community efforts that enable people to share their data sets, annotate their data sets, so that fluids in general can have an edge in this, like the data world we are moving into?
Yeah, Pranshul, thanks for raising this point. And I rushed towards the latter part of my talk, so I went through this really quickly. But getting a data set in a shareable way and putting it into a library is really expensive. We're talking about now time resolved data also across many cases so that we can test for generalizability. And that is going to be enormous compared to what we're used to. And let me just mention one thing is that this is going to require not just help from the university, but something from, let's say, the government or the industry to see if we can host these things so that it'll be of a long-term use, right? It's not free to host these things, simply put. And going back to your question, if we have these data sets, I think we can now start training and testing in a proper way, right? And I think if you want to talk about generalizability, we usually talk about trying those testings in one lab. But what we really want is to see if we can get generalizability across different cases. And that might span different data sets that might come from different places, right? Now, I think we should try for different parameter sets first and see what we get. But we can also try to see if we can go to a completely different data set that we get, let's say, from a different lab or a different setup, and see if we can test it. I hope I answered some of your questions here.
I think I'm looking for like, are there any frameworks for it? Because experimentalists have like really, really different setups. And we are also not talking about a single task. There are a lot of diverse set of tasks that we all like put under fluids in general. But how would someone go about creating a framework of validation? So coming from a PIV point, we had PIV challenges in the past, but I don't see any major efforts in this direction anymore.
Yeah, so the way I think is, I mean, the simplest thing is you try to come up with, I mean, I think this is going to be problem dependent, right? And if it's problem dependent, that's okay, but you have to figure out, okay, what are we doing the testing for a certain type of flow problems? Once you have that narrowed down, then I think you need to talk about what are the variation in the operating condition that the user or the researcher care for. That could be Reynolds number, it could be flow condition, it could be other types of disturbances that you care about, and that might vary, right? And you can take some as part of the training data set and try to come up with a, I would say a rigorous model, and you'll have to see if you can train outside of those operating conditions that you consider to see if it's indeed still useful, right, applicable. And if that's the case, I think you can show that your model is fairly good, right? But you can then think about like, okay, we only considered, I don't know, let's say turbulent flow over this type of wing. That wing could completely change and see if you can expand your model applicability. And that's, I think, an area of research that is going to be pretty interesting over the next few maybe years or maybe a decade, right? And that's probably where the power of machine learning might be beneficial.
Thank you. And we're getting a number of good questions in the chat. I might go in a little bit of a different order. Okay, so one of them, with regards to turbulence modeling, since so many traditional closure models are themselves empirical, how can we leverage machine learning models, especially for non-traditional closure approaches, such as PDF-based turbulence closure?
Yeah, so I have to admit that I am not a turbulence expert, so I'm not sure how I can answer this pretty well. But I think, and correct me if I'm wrong, anybody here, machine learning can supplement or complement some of these traditional methods really well. It might even be able to revolutionize some of the approaches here. But some of these terms or coefficients in, I would say, turbulence model, they've been tuned quite well in the traditional sense. Some might be very difficult to beat, right? But there might be ways to expand on how to, I would say, make them more problem specific in some ways or generalizable in some ways, right? A lot of the techniques that we have developed in the past in traditional ways work really well across a wide range of flow, but they're not perfect, right? We might be able to adjust for how to get those secondary effects really well, considering different types of flow conditions. That might be able to come in as input as well. So I think I can't predict what that would be like, but some of these fine-tuning details might be something that machine learning could incorporate and take advantage of really well. Yeah.
Cool, thank you. We have a question from Eugenia. Is there a reference, a book, a paper, a YouTube video that you could advise for an introductory example of the use of machine learning and fluid dynamics from an educational purpose? Or maybe reframing that, do you have that in your physical review fluids paper?
Oh, this is an easy question to answer. I highly suggest you look at Steve's or watch Steve's video series. They're awesome in terms of getting a feel for machine learning and also fluid dynamics. They cover a wide range of topics. That would be I think, the starting point that I would recommend, highly recommend. Yeah.
Thanks, Sam. Okay, Ron asks, what are the areas where CFD and ML can complement each other? So using ML to accelerate CFD or CFD to improve ML?
Yeah, it's an interesting question, and I can maybe answer by examples. Some of the things that our group, we've been thinking about this quite a bit is, for example, let's say you have some flows that you simulated, but you know that it might be slightly off in terms of, let's say, some of the statistics you want to get. There might be some ways of nudging that using some of the, I would say, corrective schemes that you might be able to take advantage of. For example, machine learning has made headways in terms of turbulence modeling. Super resolution has also made some ways of getting smaller structures from larger structures, right? You can't, you got to be careful how you apply these things, but that could be another thing. Multi-fidelity methods have also shown some interesting promise, right? You have to be careful as to how to use them. But all these techniques, I think, these are the easy ones that could be merged together with CFD.
Sorry, Elvis,
Sorry,
can you mute yourself?
You're getting recorded.
Let's see if I can mute.
Yeah.
If anyone can mute Elvis, please do.
Energía masculina también está en el hacer, en el también dirigir, en el también sostener y proveer. ¿Tú qué piensas, Emilio?
Sorry, Sam, I don't have any host access here.
I don't either. I was looking.
Beverly, Brad Rubin, can you Elvis Aguero, please?
All right. Thank you.
Thank you.
That happens.
Okay, Sam, sorry, that probably derailed your last question. We're just getting towards the end of the hour, so maybe I'm going to ask a final question. There are more in the chat, so people please
Sure.
go find Sam and co-authors at APS and ask him all of your burning questions. I'm going to ask the last one. Do you have any advice that you would like to give, kind of parting thoughts to the young researchers in the audience who want to get started?
Yeah, I think you have to have a solid foundation in fluids in all of these four fields if you want to be a great researcher, to make some important advancements in the field of fluid mechanics. So experiments, theory, and computations, you ought to try all of them. And in addition to that, machine learning. So and if you can do so, I think you can communicate very closely with one another and see what are the challenges are, what are the things you can take advantage of, how can you be inspired to build better models, and I would say get results. You also have to figure out how to interpret the results, and that's not easy sometimes, right? That's still a human thing that we have to do. That might change, and I think I forgot to mention one thing. That might change with some of the newer machine learning methods that enables you to think of like the chain of thoughts, right, to get those information. So that might be helpful, but at the end of the day, I think we still have job security for humans to understand and digest what to do with some of the insights that we get from machine learning. That's a great question, Steve. Thank you.
Oh, wonderful answer. So with that, I would like us all to thank Professor Taira again for a fantastic talk and great answers and questions. Thank you all for attending. Yeah, really exciting. Thank you.
Thank you. Thank you so much, everybody.